Thank you, Dr. Surya. Thank you very much for your nice introduction.
I'm sorry, let me introduce my my friend. So, Dr. Saurabh, he joined in our institute in the year of in June 2017. And before joining, he worked as a postdoctoral fellow in many famous US universities, as you see in the screen. And here he leads a research group with the name Functional Materials by Design. And he is a wonderful researcher in the research areas, as I mentioned here, like spintronics and energy related research. And he has very good papers, and recently he has published in Nature Communication, and for that he got award from our university. So, and he is doing a wonderful job in our university, taking our name to the next level. Sort
Uh,
it's up to now.
thank you, Dr. Surya, for a very nice introduction. And it's always looks nice that if you get nice words from your dear colleagues. So thank you very much, Dr. Surya. So let me now. I am honored to be. I'm honored to introduce Professor Yosuke Kawazoe to the audience. He's going to be our speaker for
Recording,
this theme lecture.
recording is recording.
Yeah, Professor Kawazoe is a emeritus professor in New Industry Creation Hitachi Center, Tohoku University, Sendai. He has several honorary and distinguished positions in various universities across the world, and he is Dr. APJ Abdul Kalam Distinguished Professor in SNM Institute of Science and Technology, a distinguished professor at Sarani University, Technology, Thailand, and director of ICT Center in Vietnam. He is an emeritus India Honor Member, Advisor, Professor of Fudan University, Chennai, China, President of NPO Center of Interdisciplinary Science, Advisor to Japan Gene Research Laboratory, and more. He has been invited by a number of research leading organizations all across the globe, in Germany, in US, in every corner of the world. He has been invited to give invited lectures and talks. So Professor Kawazoe has started his research in nuclear physics as a hardcore theoretical physicist. He was one of the first generation to use the computers in research, and at that time his computational skill was very much special, and he has contributed to start Education Center of Information Processing in Tohoku University in 1982. He was the first implementing this BINET in Japanese National University. Later, he was promoted to be the director of the computer center in Tohoku University. And he was invited to be a full professor in 1990 in the Institute of Material Research, and started his career by applying this basic physics background and high-level computer skills. He has been developing his own computer code for materials design, Tombow, this particular code. So anyone is interested can interact with him regarding that. So his research interest is not only limited to basic theoretical material science, development of first principle calculations, formulation and software development, new carbon. He discovered new carbon allotropes, gas storage materials. He has a huge interest in hydrogen storage, carbon dioxide storage, in metal organic frameworks, and also basically his research area covers a wide span in the canvas. He has authored over 1,200 ISI journal papers, more than 39,000 citations with the H index of 87. He has wrote about many books, around 50 books. He has produced 35 PhD students, and they are now faculties in many universities across the globe. So I visited Professor Kawazoe 10 years back in 2009, and it was a wonderful experience for me to be visited in his group and get advice from him. So with further delay, I request Professor Kawazoe to start his lecture.
Thank you, Sora, for a very big introduction of me and sharing my session. Please help my listening. Sometimes India speaking, asking me something, question, but not easy. So Sora, please help me after my talk for the questions.
Sure.
And Surya-san, thank you for organizing this very good meeting, and I'm very happy, but very unhappy that I cannot go to your place to meet you, shake hands with Sora, and drink together. It's impossible now. But yeah, we should vaccinated soon. Everybody finish the situation and physically will go to celebrate the real center of SCMS, maybe in the end of this year or something. Okay, please join us again. Okay, then I'll start my talk
Yes.
with this slide. Okay. Okay, Wanakam. This is only one Tamil vocabulary I know. Wanakam. Good afternoon, everybody. So, this is title today. Worked with Ono Mizuseki is here. Sahara, Hongo, Nanis, and uh, computer people, and Sarukrasan. He's an experimentalist. So we are working the team of not only computational material scientists, but the experimentalist and also computational people. So it is a good news for us that 2 years back, unit changed. You know, uh, unit has been used for a long, long time as a physical scale of 1 meter, 1 kilogram, 1 second, 1 ampere. 1 kilogram unit machine was in uh, France and something like that for a long, long time, 200 years of the history. But now it is becoming more and more fine. The unit is not 1 meter. Now it is becoming nanometer, and it is not possible to use such an old system. So 2 years back, really changed these units to atomic units. And this is more reliable and more universal because people changes, machine changes, but atoms are not changing. So this is the situation you should understand. So basic thing is very important for us, especially everything, me, you, machines, everything composed of atoms. So this is very good chance for us, computational material science. We can treat everything by our unit. You know, we have used the atomic unit from the starting moment when we learn quantum mechanics. So we are very much used to this unit. But the other people, something like the mechanical engineers, anybody, medical doctors, they use the old-fashioned unit of meter, kilogram, second, 1 ampere. Those are fit to human body size, but human body is composed of atoms, and we change to atomic scale, and we have very good chance. This is what I'm saying for the first slide. Okay, so this is a big paradigm shift from classical to quantum happened in the 21st century. Next one. So this is everybody shows, and uh, from classical to atomic level. So meter to nanometer. This is 9 order different scale. But from nanometer to angstrom, this is really only 1 order, but it's a very big, the optical properties. If you want to compute the band gap, we should use quantum mechanics. But in the nanometer scale, it is in the sense classical region still, people are etching the uh, integrated circuits by optical technology, and molecular level, it says molecular atomic level, but basically we can treat them classical way, potential between atoms to atom. But in the electric level, it is completely different. It's a classical to quantum changes in this only 1 order scheme. So now we are shifting from this level to this level. So 9 order magnitude is not so much problem. People can come very easily from meta scale, classical scheme to molecular dynamics. But molecular dynamics, we use some phenomenological assigned potential. It is not ab initio. So ab initio calculation basically change the world because we have no parameters from experiment, and basically we have all knowledge. All knowledge means the governing equation is the Schrödinger equation, quantum mechanical equation, and potential is simply the Coulomb potential between atoms, nucleus, and electron. Nucleus, electron atom potential. Those are all Coulombic. So everything we know. So what we should do is to solve this equation. So for a long time, in starting from the quantum mechanics 100 years ago, it was invented, and solid state physicists, computational chemistry, those people focused in these 100 years explain the experimental observed materials properties. Basically they explain, and they never produce something new. But now it is changing. You use ab initio calculation and predict something new without experimental observation. But we should be very careful. This is my talk first. So when I started, no name, at least in Japanese vocabulary, corresponding to computation materials, or I have invented, but not much computational power. So only something like very simple MD simulation was the first 30 years ago. But the computer power has been increased in these 30 years. It is called Moore's law. In 5 years, 10 times faster machine comes. So actually, in these 30 years, 1 million times faster than when I started. So it's a very big change. And now we can treat, for example, molecular dynamics can treat really big number of atoms. People are saying about whole body simulation, all the body, all of human body, they will put into the computer in the atomic level, something like that. And the density functional theory now, for example, Surya-san did calculation for maybe several hundreds atoms, and we can predict the new materials, and experimentalists follow to generate it. So nowadays, only people are wondering how many atoms they can treat, but is it good enough to be confined within the density functional theory? No, no, it is not so simple because to solve the density functional theory, we need exchange correlation potential, and it is in the sense phenomenologically set sometimes, something like plus u and hybrid functional alpha to fit to experiment. So better approximation than DFT, for example, GW approximation or time-dependent density function theory. These are far better than the DFT. DFT is very good for the ground state, but mostly experimentalists observe the properties not in the ground state. For example, band gap means excitable to the ground state transition. And chemical reaction, everything happens not in the ground state. Catalytic reaction, excited state is the most important, something like that. So not only increasing the number of atoms, but we should shift to the next scheme, which is better than the present day. So in the 21st century, based on the you know computer power, we can increase the number of atoms. It is of course important, but next generation, next state, as I have told you, Surya-san, Sora, your future is bright, but you should come out from the present scheme to next scheme. So this is a example that big progress really happened. What I mean is that speed of the computer is the order of nanosecond, and our brain can treat only zero point 0.1 second. This is based on the chemical information movement from our eyes to the brain. It's not so fast, but the computer can compute very fast. And the problem happened recently is that the computer memory size is now more than people's neurons size scale. We have about 10 giganeurons in our brain, not much different from people to people, about 10 giganeurons. But computer has even, or PCs has terabyte of the memory. What does it mean? Computer can remember, store everything. So the uh, old-fashioned people, most important thing in the university means understand, remember everything. But now it is not possible. We can remember, recall about 20,000 basic vocabularies, but computer can handle many, many. So this is the reason why qualitative change happened, not quantitative. Qualitative means, for example, computer now generate artificial intelligence consideration. They make something different from what people are considering. Something like chess game player, computer chess game is player is better than human chess game champion. And in our region, it's also coming. So it's a really big paradigm shift in the 21st century. Okay? In our field of computational material science, now molecular dynamics reached to the, sorry, this is 20 years ago. 20 years ago, MD only 1,000 atoms, density functional theory maybe up to 50. And this is one example. 20 years ago, I have made a movie of fluorine into nanotube. This is a maximum in the classical molecular dynamics. And the C60, this is our invention that contains lithium ion inside to make the dipole moment. And experimentalists could not distinguish that lithium atom is incorporated into the C60 or outside of C60. And we have computed, and Ono-san walked by using Tombow, that this is the real situation, that lithium ion bombard and coming into the C60 and trapped inside, and C60 is recovered. So this is our initial calculation at the time, but we had very big supercomputer as our PC, so we could did it 20 years ago. Nobody could do it. So computer power is also important for advanced technology. You know, this is everybody uses the phonon calculation, ab initio phonon calculation. This is I invented 25 years ago with Parinsky and Lee, and everybody used this formulation to check stability of the system. So based on the density functional theory, we can set up atomic constructions, atomic structures, but we should confirm those atomic structures are stable, and applying the phonon calculation, there should be no soft phonon, that this structure is broken, not stable. So if there are no soft phonon, the atomic structures predicted by density functional theory, we can say this should exist. So this is the basic idea up to this level. So present day standard changes. So for example, the DFT such as VAS program uses pseudo potential with plane wave expansion. But maybe 100,000 atoms we can play with. And GW approximation is implemented in most of the such kind of ab initio open code or commercialized code. But many people believe that GW is too heavy for normal use may be limited up to order of 10 atoms and not so much interesting. But you know, computer power is increasing, and for your future, you should shift to this because we can estimate without any parameters the band gap, for example. And the subject TDDFT, this is what we are working using the Tombow code. It is only possible because in the bus code and other TDDFT means there are only change from energy, space to time cost, reducing the computing time. And the chemical reaction tracing, most of the people use the NEB method. This is an energy surface estimation. But the chemical reaction never happens on the Born-Oppenheimer adiabatic regime. We should keep the electric states also excited. So up to present, all the computed barriers for this stage to another stage is too much higher. There are no such kind of barriers. As you know, in the quantum mechanics, penetration, they pass through the barrier, it happens. Okay, so this is the way we can distinguish ourselves from other groups. This is the aim of Asian Consortium for Computational Material Science. Develop such code and support the project of you. And for example, absolute energy calculation, this is not possible by pseudo potential. And as I told you, out of the adiabatic approximation, such kind of things, those are the advanced theories more than the present day standard commercialized, and you can distinguish yourself. Okay, this is one example for the GW result for the this is a crystal of diamond, and we can really estimate without any parameters the red circle for experiment, and our computed result are within this red circle. So this accuracy in absolute energy we can compute. So please consider for such kind of, and this is recent example computed by Talgat, and the LDA-PB for indium uh, nitride gives the negative, this is a metallic, no band gap, and the hybrid potential makes the experimental value, but it fits to experiment, not Gibbs. But these black circles are our estimations without any parameters, and this can be done by the self-consistent GW. So such kind of things now we can do. So van der Waals potential by Vladimir, he did very good work. For long time history, van der Waals is introduced in high school. Everybody knows, but nobody computed the C6 coefficient, dipole-dipole interaction part. We were the first. I was much astonished to understand that we were the first to estimate C6 coefficient without any experimental parameters. So we are very happy for that. But nowadays people use density functional theory with van der Waals exchange correlation. What does it mean? Van der Waals and exchange correlation, there are no relationships, but people use such kind of phenomenology to discuss about the layer distance, something like that. But we can compute this without any parameters. Okay, so this is one example, the chemical reaction. So chemical reaction, especially catalytic reaction, we should keep electronic state kept excited at the temperature, equilibrated, not only the atomic motion, but the electronic state should be in the same temperature. So we did it. This is also 10 years back. Hydrogen molecule H2 comes to be separated. It's called a spillover process to store more hydrogen. So these kind of simulation, mostly people use kinetic effect to break H2 to HH, but we have no kinetic effect, no means, no initial kinetic energy, but H2 breaks into H and H. by the effect of the nickel diamond catalyst. Okay, so this is the one which we have done. The in 20 femtosecond, we firstly excite one level, one electron, and then it comes and change the structure. So electric band structure changes. Okay, so now it is coming to the main part of the molecular, materials informatics. Now theory first. This means my background as Sora introduced me. I graduated elementary particle physics, where always theory first, and experimentally should certify what theorists predicted. So it's good chance now in the 21st century, we computational material science predict something, and let experimenters to follow, realize our our predictions. Okay, experimentalists, industrial researchers, you know, they can only modify the existing materials, but we can completely change the situation, and we can free to search new compositions, not confined by previous knowledge, previous experiment. But there are too many cases for human to handle. Computer memory speed is far better than human memory size, human computing speed. So we should let computer to work. This is an artificial intelligence consideration, and their support in our computation material science is called materials informatics, MI. So MI is very, very helpful for us, and the subject we should select for the first. And many people are now working on the materials informatics in our field, and there are two good candidates for you if you plan to start this business of materials informatics. I recommend such kind of thing. For example, 2D materials is called MXene because structure is fixed and you can change the atomic species. So we can generate many, many structures easily by using computer. And this is Mohammad Kazayasan's work. And we are the first to discuss about the functionalization of MXene theoretically. And we predict many properties. MXene plastin basically metallic, but we add some element, oxygen, something. And then we modify the properties to be semiconducting, magnetic, even thermoelectric, something, something. So these are really our prediction. And the experimenter tries to uh, functionalize vaccine, and really they have found such kind of properties. So we are very happy for that. And another one is the simple one. Simple one means less number of atom species. For example, carbon is very good because only one type of atom of carbon. So we only consider the geometry, not atom difference. If there are many different atom species, the situation becomes more difficult. But for example, as Sora said, I worked, for example, pentagraphene, and this has the first one having the negative Poisson's ratio as a stable material. So we're very happy. After this invention 5 years ago, already 400 papers cited our pentagraphene work. So this is something like that we can do. So this is a good example. 10 years ago, Professor Sarkura is an experimentalist in Osaka University, requested me to find out ultra vacuum, is called vacuum ultraviolet, more high energy light emission material. So he said, experimentally too much time consuming and too much costly. So we started throughout the periodic table. At that moment, 10 years ago, many people are working for Gary Mass and so on. So we started to find out the lighter element. Lighter element means wider band gap. So fluoride might be good. It's a challenge because 10 years ago, almost no experiment. Only one experiment exists was the lithium yttrium fluoride, only one. And we have surveyed many types of fluoride things. On the right, you can see magnesium aluminum fluoride, magnesium gallium fluoride, and computed many things. And Dr. Nishimatsu worked with this one. It's very time consuming and tedious work, but he has found several good ones. Good means direct band gap and wider band gap. And these are the very good materials. For example, lithium, calcium, aluminum fluoride, and so on. So experimentalists really synthesize these, and it is a material having very wide band gap and a direct band gap. So they made these as uh, commercialized material, and actually these materials are used. So in 10 years, we computed and predicted new good material, VUV material to experimenters and synthesize and commercialize. So it's a kind of very good success, but serious problem is that by DFT or any other phenomenological method, we cannot really predict the real band gap, the emission of the color. So at that time, in the MI vocabulary, forward prediction, we compute. So, you know, people said band gap engineering, but engineering should be based on confirmed theory. So confirmed theory, DFT is good for ground state, predictable atomic configurations, but not for the band gap. So we should shift to GW. So the next subject came last year to us, and Mizuseki is working on that subject. And, uh, among RGB, red, green, blue, red and green, uh, sorry, it's a mistake. Red and blue strong, this is B. Red and blue strong emitting diodes already established by Professor Nakamura and so on. So requirement is strong green color emitter. This is not yet found. And RGB with the same material system, they can generate three colors emission by using the same system. And experimentally, 3,5 compound semiconductors have been studied very well, so they can generate by changing the composition, the ratio. So this is what they requested us. So we worked, but GW for this system is too much for us, too much time consuming. So Mitseki worked to running. Running means the neural network running for DFT to GW. We compute or experiment the data from experiment of the band gap, and those are used as a teacher knowledge, teacher's data, and then we compute many DFT calculations and fit to GW result or the experiment. And then we generate many and prepare a lot of data computed by DFT, but the band gap are modified by this neural network knowledge. And then this is backward prediction. Experimentally said this energy, this color, this is the green color. Then we can search among the computed result and give them the result. This is the materials informatics method, backward prediction. This is what we are doing. So there are experimentally very
Hello, Sensei. You
finish,
have 2 more minutes. Hi.
Okay, finish in 2 minutes. So miscible, immiscible. These materials are really immiscible region is wide. So only at the edge. But we were successful. Mizuseki worked, and these are the regions where we can have red, green, and blue. So this is what we have done, and we are very happy for that. So conclusion comes that materials informatics is possible, but we should be very careful. you know, important thing is that deeper understanding of physical chemical properties. This is mainly human first, not only running the software existing, but we should consider and theoretical development of basic theory ab initio is most important, of course, but still the level we should make better level of the ab initio calculation. And also, people are now interested in the Python, the AI part only. But the basic thing, what we can compute, is still the program by Fortran. So I should say thank you for supporting this material informatics project by Kyushu University Computing Center and HPCI. They give us 1 million node hours, so we can compute a lot of cases. Mika Nandri, Mika Nandri, sorry. Thank you very much.
Thank you, Professor Kawaze, for a very nice and informative talk. And you always, when actually I, in particular, when I always listen to your talk, I always learn something from it.
Oh, thank
Uh,
you very much.
so the question is open for, the session is open for questions. So you can directly raise your hand and ask questions, or you can post in the chat box. So I can read it for you. Uh, let me check if there is any question in the chat box. So far, no. Yeah. So any questions? Any questions from the audience? You can raise your hand. Any questions? You can post in the chat box, or you can ask. You can raise your hand. I can ask you to unmute. Okay. Okay. So let me start. I have a questions, Professor Kauze.
Yeah.
So now there's a new paradigm shift that people are using machine learning and artificial intelligence, deep learning, in discovering new materials and new discovering new superior properties, or designing new materials that not yet been synthesized or not yet been thought of.
Yeah.
What do you think is that algorithms that we are using from the information technology domain, will it fit to our need, or we need to do some more work on the algorithm part of the machine learning that can fit to the material science?
Machine learning part, as I've told you, programmed by Python and so on, is a kind of, we say, higher level of the program, but in the basic things, this is what I stress today. Important thing is how to compute first and store many, many data, and then we can pick up by using AI technology. But the important thing is that those stored data are reliable or not. So we should generate many, many data. Computer speed is good enough. And then what we should do is very careful selecting good data. In the most of the MI technology, people compute many, many DFT data, and some of them they don't like, they discard. What does it mean? Those should have also some good meaning, maybe, but only within this region if the value is not what researcher expected, then they cut this data. No, this is not a good way. What we should do is that compute all the data with requested necessary accuracy, and all the data should be equally reliable. And then we should not cut this data. If people are cutting data by some criterion, this is artificial, not really theoretical. Theoretical computational material science for applying the MI, AI technology, we should be very careful that all the data we are generating are reliable, not compared to the experimental observations. So we have good confidence and fight with experimentalists what we are better than you are doing. Experimenters always having not completely pure material, and they they make some mistake, and uh, depending on the machine. But what we are doing is without any such kind of confinement, we can generate. But important thing that what we are predicting is good enough. For example, the atomic configuration structures, we can say with the DFT calculation and the phonon stabilization checking of the soft phonon, we can say this material should exist. And the next step is that this property, for example, band gap, we should compute by reliable
Yes.
theory. Means the theory can generate exactly the band gap. So without any experimental observations, something like plus U, hybrid alpha, and so on. So then you have good confidence and you can fight with experiment. If their data, experiment data, and our prediction not much, I can say, oh, you made a mistake. Please come back, experiment lab, and do it again. This is what you should do. My recommendation to Sora.
Yeah, yeah, that's a very, very, very cool.
Hello, Sensei.
Yeah.
Professor Das has one question.
Oh,
Yeah. Hello, Yoshi. As usual,
hey,
it was a great talk. Thank you very much for the talk. Yeah.
thank you, thank you.
I just wanted to, I mean, pose one a query, a very general query. There is a lot of things we are hearing, and there is a lot of progress on quantum computers. Okay, there's a lot of progress today
Yes.
on quantum computers, and we are thinking of achieving even up to something like 100 qubits quantum computer. Okay, maybe in near future. Okay. But there have also been a substantial amount of work which is going on stochastic neural network. Stochastic neural network, where we do basically the probabilistic approach. We take the probabilistic approach. And, just some time back, there was a very, very beautiful talk which I listened to in the same conference from Hideo Ono of Tohoku University. So Hideo Ono mentioned about the probabilistic circuit, P circuit he calls it, and he calls about P bit instead of Q bit. P bit is basically a classical concept based on probability, stochastic thing. So there is no quantum computation involved. Now, in a P bit, you can go to 10 to the power 9 P bits, whereas in a qubit, you can go to 100 qubits. Now, with all your experiences for the past so many decades, will you be able to make any comment as to whether the quantum computer will really be able to compete with the classical computer, at least in immediate future? What do you think?
GP, quantum computing is suitable only for some circulating salesman's program or the encryption, very limited area where not much memory is requested. But for our case, we need big memory. And, as you say, 100 qubit, it's impossible for us to compute the quantum mechanics. So the quantum computer is quantum, but quantum computer is not suitable for quantum mechanics.
So we have to go ahead with the classical computers, at least in the coming foreseeable future. That's what you're saying.
Yeah, GP, we can contribute to speed up the clock speed, as you know, 10 years, no increment, always 2 gigahertz, 3 gigahertz. Because we are using silicon technology. So this part we can contribute from the material side. And my good friend, Professor Omi, he said up to 50 gigahertz, we can increase the clock. And then fundamentally different thing will come. So this is something like the computer speed is increasing nowadays, people say, but not speed. It is a amount of computer, Speed is the same, but many computers, small CPUs, we say core and node, but the speed itself is the same in these 10 years. But we computation material science can predict some better material than silicon, for example, and change this computing speed, real speed, clock time from 2-3 gigahertz to something, one order, two order higher. So this is another very, very important contribution of us.
Hello, thank you, professors. Actually, we are running out of time,
Thank you.
so
Thank
we
you,
can
Professor
go on.
Kawaze. So it's a very nice and informative talk. Let's thank the speaker again. Thank you, Professor Kawaze.
Hey.
Now we are learning late, and we're going to move into the next talk.
Sensei, you can stop sharing your screen.
Yeah.
Oh, sorry. Yeah, help each other. This is one last requirement to our friends.
Yeah. Okay. So I can share my screen, Surya.
I will do.
Okay. Okay.
Is it okay?
Yeah. Is it okay? It's fine. So okay. So let us move to the next talk. It's an invited talk. It will be a 25 minutes talk followed by 5-minute question and discussion. And this talk will be given by Professor Duak from Theory and Modeling Department, uh, Coulomb Center for Fusion Energy, United Kingdom Atomic Energy Authority. He's very well known to us. Actually, we meet in different conferences at different organizations. And he did his PhD. Professor Duke did his PhD from CNR's Grenoble in 1986. And then he's recipient of many awards and achievements, like a Principal Investigation Award in Eurofusion program, working at Coulomb Center for Fusion Energy, academic visiting fellow at University of Oxford from 2005 to the present. Then he's OCAM OCAMAC fellow at the Department of Materials, University of Oxford, visiting professor at University of Pontrose, France, and visiting scientist, University of Pennsylvania, and so on. So he published more than 190 publications with H index 39. And his area of interest mostly cover modeling and computational material science from first principle models, and mainly focused in radiation-induced transformation and radiation-induced phenomena. He's also an expert in multi-scale modeling, linking material science with the physics, chemistry, and engineering applications in order to reduce uncertainties in predicting complex phenomena. Today, he is going to talk about nano defects formed under neutron irradiation in fusion reactors, first principle based modeling and experimental validation. With that brief introduction, I would like to request Professor Duke to start his presentation. Sir, you unmute yourself. Professor Duak, you unmute yourself.
Can you hear me?
Yeah, fine.
Oh, thank you. Before I making my presentation, I would like to thank the chair, Professor Gross, and also the main organizer, Surya, for excellent virtual conference, ACCF conference symposium. So what I'm talking today essentially to see whether from Professor Cavazzoi talk to see whether the ab initio calculation can be extended to look at the body with billion of atoms essentially in fusion reactor here. And please keep in mind about this snapshot, which is showing here its plasma created by the nuclear, the DT fusion reaction in fusion nuclear, and how is the plasma will be exposed to affect on the machine properties on the first wall here. And so that is that I'm try to do in the next 30 minutes. Before that, I think it is right again to see the ICCMS activity is still going on despite very difficult times. I remember the last time that I've been in India is last year in the International Conference of Machine Genome, and it was the last conference I was attending physically, and so it is good that we continue to work on ICCMS community to promote the computation material science. Few years ago, I also organized a team meeting on multi-scan machine modeling for sustainable development in Vietnam. So the activity on that, my main activity, as Professor Roche mentioned, is on the multi-scan machine modeling. Essentially, we try to use a high fidelity multi-scan modeling based on first principle. And it is come back to my initial work at University of Oxford with Professor Pettiford, which is showing that the hierarchy of multi-scan modeling is very complicated because we are working on machines, computation, machine science, which is essentially a link between not only physics and chemistry at electronic and atomistic level, but is also need to be linking with the engineering level. And so in this slide show something illustrating in the last few years, we show that it is possible to use this scheme to link not only with physics, is in this slide that we predict the motion of one-dimensional loop dislocation loop moving in irradiated materials by quantum mechanics prediction, which is published in Nature Materials last year. And so how is linked machine with physics is that we able to predict the outstanding radiation resistance to the short range order parameters in the high entropy alloy, and this appear in that the Los Alamos laboratory detected the same material which is very high radiation resistant. And going to engineering side, so I'm showing slide here, a summary of the DFT prediction on elastic modulus chance under irradiation. And you cannot see here, but I'm sure that you can see in Acta Material paper that we predict about 2% reducing the elastic moduli under for tungsten and helium implantation. And it is detected experimentally, and it is perfectly showing that the ab initio calculation can go to look at the engineering problem. So what I'm talking today is another problem, which is happening in fusion reactor, which is that under neutron generation, there's the effect of transmutation. And it is important to mention that transmutation effect, for example, here I mentioned about tungsten, which is producing transmutation in terms of the next atom in periodic table, and I show in next slide, is rhenium, osmium, tantalum. It is depending on the dose, which is the measure of displacement per atom. And the key point I'm showing here is that so far the neutron irradiation is happening in fission reactor and not in fusion, because we don't have the fusion reactor yet, but we have some prediction from neutronic, which is showing very low transmutation rate, whereas experimental in fusion reactor essentially is going to produce very high. So in absence of the fusion reactor, how we could predict the phenomena related to transmutation at very low dose. Okay, and that is the key point that I'm addressing here. So what I'm showing here is that I also show some part of periodic table, but under irradiation, and I'm focusing on tungsten. And tungsten under neutron irradiation, which is producing by deuterium and tritium nuclear reaction, is produced very high energy. And the high energy is exposed. Okay, so it is going to change the material properties. For example, if we use the first one as a tungsten, then after 2 years, then there's some amount of the radium, osmium, and tantalum is producing, as I show in first slide, it's showing here, and it is evaluated is that changing the composition as function of time, and the time here is year times. Okay, so it's very slow neutron reaction, and it's coming very long time, and it is very important that we understand this phenomena because it's changing the material properties of the first one in fusion reactor. So the thing is that we can use some experimental evidence from the fusion reactor with low transmutation rate, which is done by my PhD student here. And what I'm showing here is to show your atom probe tomography experimental observation of recent discovery of the phenomenon called the void decorated by transmutation. So here is atomic probe tomography figure showing that inside of precipitate you have the radium, which is showing in red here, and the osmium is showing in green, is forming under neutron irradiation. It is also in single crystalline tungsten, but is also in polycrystalline tungsten, which is showing here at the grand boundary. You see that accumulation of the radium and osmium around at the grand boundary. And what is important here is atom probe tomography picture here is for ion irradiation, but it's showing that if you have the presence of both radium and osmium, then the behavior of precipitation is quite different. If you have the only radium in binary alloys, then you can see that the radium is main precursor of precipitation. But if you have osmium coming on, then you have mainly the effect of the osmium in precipitation inside of the radiation-induced precipitate. And it is the small amount of osmium is become very important. So we try to understand what is happening here. And here is showing the image of high resolution transmission electron microscopy of the void showing in tungsten, which is black spot here. And if you zoom into the high resolution technique to detect radium and osmium, you can see that inside of void you see the radium in red decorated, and you see because the amount of osmium is very small, but you can see some amount of osmium inside. Essentially, you see the inside precipitation, you see the correlation between radium and osmium inside. And in terms of nano defect created in the neutron irradiated structure, you see the big void, something like 10 nanometer scale here. And it is important that the people is detected in the in the 110 faceted. Is void, nano void is forming in faceted way. And the key consequences of this defect is that you see the contribution of voice and contribution of the precipitate in the hardening of the machine, which is really important at the high temperature. And so it is important to understand the origin of precipitate and the nature of something like void forming in tungsten under neutron irradiation. If you have the polycrystalline simple sample, then you can see that the void is somehow in so-called denuded zone, which is away from the grand boundary. So that phenomena that we also want to understand why it's happening, if possible, from ab initio calculation. So it is very big, large scale, engineering scale. Summary of the experimental observation is that for the sample that we look is in the tiny phase diagram of tungsten, osmium, rhenium is essentially in BCC solid solution limit of tungsten, and the radiation induced precipitation is only happening in this region. It is so that's why we call anomalous, because happening in normal alloy, ternary alloy, you have the BCC phase, but even under irradiation, you see precipitate forming or second phase forming in the BCC region. So we call that anomalous because it's inside of BCC region and it's not in the sigma phase or as a intermetallic phase in alloy. So what you try to do in the computation approach is we adopt so-called the alternative approach. Conventional approach is normally using kinetic Monte Carlo simulation a priori, that you understand the equilibrium phase diagram and you try to predict the kinetic of motion of the atom under irradiation to reach the conventional phase, like the sigma or the chi phase in tungsten rhenium phase diagram. The approach that I'm using here is essentially coming from more alternative one, which is generally that we predict the free energy of the various potential phase in presence of induced defect by radiation. For example, if you have the voice, you have the super saturated presence of vacancy at high temperature, and you have the super saturated of institution defect at the low temperature in forming the dislocation loop. So if you can build up the free energy approach and minimize the free energy, including the defect, and then you can predict different phase, including the anomalous precipitation that we saw in the previous slide. So that is the approach that we call the thermodynamic under irradiation, which is not so new. It's coming from Jacques Martin early on driven alloys, which is considered alloy under irradiation and its chain properties. But at that time, with our initial calculation, it is quite difficult to see what we can predict realistically. Sorry, I cannot go to okay, so yeah, so coming from ab initio calculation, it is coming back to Professor Cavazzoli mentioned is that HN correlation function is really important. And for tungsten, it's a very important problem in predicting the defect properties. For example, predicting the voice in tungsten is not easy because the formation energy even predicted from DFT calculation with HN correlation function is predict about 3.3 for point defect vacancy, whereas the experimental data is about 3.5 or 2 until 4 electron volt. So the missing thing is because we treat the vacancy HN correlation function and nearby to the vacancy defect is not properly correct by using HN correlation within the PBE, for example, functional. So we need to go beyond the PB function and to see to treat inhomogeneously the electronic charge around the vacancy or cluster of vacancy. So we have quite a lot of work doing that and realize that from DFT calculation, the binding energy between two vacancies is negative, meaning that they're not attractive. So from classical theory, it's not easy to form the void from divacancy. So we need to go to cluster vacancy. That is we try to do, and that is we try to say that the binding energy of the vacancies of the vacancy cluster is starting to build up from the 3 vacancy, 4 vacancy things. So it's essentially quantum mechanical effect of even from the point defect calculation, we see the point defect have the quantum mechanical effect. And when we go to migration of the vacancy cluster, we see that it is not easy to use classical potential to predict because, for example, if we want to look at tri-vacancy here, okay, then you can see that the sudden point configuration of tri-vacancy is go to the minimum and somehow is not can be not predicted by the conventional intermediate function. So essentially there are many quantum mechanical effects only when you go to detail and you can see that it is affected the quantity or quality or accuracy of the understanding, for example, of the void in tungsten. So we use first principle approach to construct the Hamiltonian. So essentially we mapping the interaction parameters from DFT calculation in order to get these interaction parameters and try to use these interaction parameters to do Monte Carlo simulation at high temperature. So we try to transfer ab initio to Hamiltonian, and then from Hamiltonian using in Monte Carlo simulation to treat the phenomena at high temperature. Essentially, I use the matrix formulation, which is recently developed mathematically. The key point is that I'm showing here the short range order parameters I mentioned in the next few slides, which can be presented in the matrix formulation, which is important for multi-component system, for example, for alloy with many elements, and also including the defect. So it's quite a complicated thing. We need to have the mathematical tool to compute it efficiently. So for example, I take here the Hamiltonian for the tungsten, rhenium, osmium with vacancy, which is already 4-component system. And we can build up to get the effective cluster interaction here in falling Hamiltonian, which is somehow we independently check it with so-called another DFT independent set to see whether it's predictive power of the our cluster expansion build up from the previous slide to see whether it is good. Then checking the course validation with different vacancy cluster and vacancy cluster with rhenium and osmium, we see is quite a satisfying result, taking into account that the independent DFT data is constructed in a different way as we did before for mapping to Hamiltonian. For example, in terms of energy cutoff, in terms of the function, and for example, previously for class expansion, we use a semi-core electron pseudo potential, pole potential, whereas in the independent data, DFT data, they use without semi-core and with low energy cutoff. So uncertainty from DFT, even from DFT calculation, quite a lot of uncertainty, because if we do DFT calculation in different way, then and maybe even class expansion Hamiltonian can predict is even better than DFT because we're not doing in the same DFT data set. So what is the first Monte Carlo simulation is to compare between rhenium, osmium, tantalum interaction with the void in BCC tungsten. So the most important thing here is that I show a two temperature. About here is a Monte Carlo simulation. Red atom here is rhenium. Green here is osmium, and yellow here is tantalum. Okay, and we can see that at 800K or even at higher 1,200K, we see the void formation in our simulation, in Monte Carlo simulation. And most importantly, we see that the rhenium can be correlated with vacancy in vacancy cluster, and osmium can also strongly created decorated with vacancy, whereas tantalum is not decorated. So we see the different picture for three different solid elements. And we can understand that very simple from DFT calculation. For example, if we look at the binding energy of single vacancy with nearest neighbor rhenium, osmium, and tantalum in the BCC lattice, you have nearest neighbors that you can see that the binding energy of vacancy with rhenium is positive, meaning that they are attractive. Whereas osmium is also positive, but is stronger than rhenium.
Hello,
We're
Professor.
comparing.
Hello, you have 3 more minutes.
3 more minutes. Okay, so I'm picking up. So you can see that for tantalum, we see that it's negative, that they're not binding with vacancy. Importantly, is that it is also shown in atom probe tomography picture that tantalum is not essentially forming in precipitation with rhenium, and it is essentially behave quite a different. So in terms of, because we're looking at thermodynamic under irradiation, we see that the formation of void can be understood from the free energy calculation. For example, here is showing the entropy configuration is calculated from this formulation, and see that at high temperature from this ordered configuration, you see that a jump in entropy in both tungsten, rhenium, and vacancy, tungsten, osmium, rhenium, vacancy. So we see that there are jump in entropy, which is the thing is happening at high temperature to form the void in tungsten, and it is happening in what we see in simulation here. We see the void at different rhenium concentration and different vacancy concentration is happening when we're quenching down from the 2,500K to the very low temperature. And this feature can be showing at the irradiated temperature, which is corresponding to experiment that data that I showed earlier, that you can see that we have 3 voids happening here. And if you look at the void separately, then we can see that it's faceted in 110 direction, which is exactly that high resolution TM image is showing early. But here we show quantitative picture of the void formation from ab initio calculation. If we have osmium coming in, because I have few minutes, so 1 minute, so I can only go. But the key thing is that if you have the rhenium entering into the equation together with rhenium, then osmium, even at very low concentration, is dominating in void decoration, as you see green here. And what you see here is very sensitive to osmium concentration. We see the short range order between osmium and rhenium is changing the sign from positive to the negative from high concentration of osmium to low concentration of osmium. So it is very, when it's negative, it means that rhenium and osmium can be correlated inside or precipitate together. And that is exactly we produce at the very low concentration of osmium, which is exactly transmutation concentration that we see in the fusion reactor, that is only produce only very small amount of osmium, but we see the correlation between osmium inside a precipitate due to the negative short-range order. So comparing with atom probe tomography, we see the same picture, that there are also correlation between them. So one of the last slide is that we also can model the segregation of rhenium and osmium to the grand boundary, whereas the void is segregated from grand boundary. So it's demonstrating that the model can predict also the denuded zone in the polycrystalline tungsten sample. So the conclusion is that you can see in my presentation, the takeaway message is transmutation is producing the new element in material, and it is causing many problems for material under neutron narration because it's changing the composition. In absence of the neutron resources, the multi-scan modeling from first principle is really it's important to tune for understanding the origin of nano defect formation, such as void decorated by rhenium osmium. The new computation tool allowed to predict inside of nano defect is a correlation between different solid elements in terms of short range order. And we also able to compare with experimental data. So, and the tool is extended to look at the grand boundary segregation of solid atom and also the void formation away from the grand boundary. Thank you very much for your listening attention.
Thank you, Professor Duke. So the session is open for questions. Please raise your hand or type the question in the chat box. I can see only one question by Mr. Kumar. He is asking why the vacancy formation energy is underestimated.
Say
Why is the vacancy formation energy is underestimated?
Okay, so the point is that if we treat the okay, so it's very sensitive to exchange correlation. And if you treat the electron density in homogeneous way, then it is underestimated in presence of voice because the situation with, for example, PBE function form is using, if you use, for example, even you use homogeneous distribution of electronic charge, it is not correct way to understand the electronic distribution around the empty space in the system, and that is why it's become underestimated. If you look at DFT calculation of vacancy in metal, then you can see it's always underestimated experimental data, and you need to go to higher level of exchange correlation function in order to correct the homogeneous effect, or you have to include the inhomogeneous electron distribution to capture the formation of vacancy energy correctly.
Hello, Duke. This is Vijay here. So I have another question. Can you hear me?
Who is that, Vijay?
Hello, this is Vijay here, Duke. Hello.
Yeah, I can recognize your voice. Yes. Hi.
Yes. I have another question. Do you have oxygen in experimental condition under neutron irradiation? Will there be oxygen present in these materials?
Yes. So it's the oxygen, nitrogen, or carbon is present in material is very small quantity. So is APPM level is million. It is very low concentration. So I'm not showing here, but in another work, we look at the effect of oxygen, nitrogen, and carbon at very low concentration, and appears that it's even low concentration is also affecting quite strongly on precipitation under irradiation. So I'm not showing here, but you're right that oxygen is playing very important effect in forming. And I am not showing here, but in another work is showing that even.
That's right. Yeah. I raised this question because we have done some work on tungsten recently, and in the presence of oxygen, BCC tungsten goes to A15 structure.
Exactly. So it is already mentioned in DFT calculation by Max and Slaughter in Netherlands somehow ago. that if you have a very small amount of oxygen, you go from BCC to A15 phase, which is the metastable phase of the BCC.
But no, it
tungsten.
becomes stable actually.
Yeah,
It becomes lower in energy with oxygen.
Yeah.
A15 phase becomes lower in energy.
Yeah.
So I
You're
was just
right.
wondering that you are showing these nano clusters. So I was just wondering that if there is some oxygen present, even though in a small quantity, and you have rhenium and tungsten makes tungsten 3 rhenium A15 phase. So there are maybe more complications to properly understand this.
So it's certainly more complicated because you extend the number of components that I mentioned earlier into, beyond 4 or 5, 6. So you need to have, essentially, you need to have a computation tool to treat many components. That is key point. And if you have these tools, then you can treat at any composition and any temperature with the Hamiltonian bin up with ab initio calculation.
Okay.
I answer to your question.
Thank you.
Yeah. So as you're being wait, we'll take one more questions. The last question from Professor Kawazoe.
Thank you. Duke, in the nuclear power station, normal ones, the shroud is also damaged by neutron irradiation. Then iron always put vanadium, for example, for self-heating.
Yeah.
And such kind of self-healing of your system is also possible.
Yeah, so I'm talking only here. I'm taking only one example of one component in fusion reactor, which is diverter, which is I think in first slide I show. In the structure material is essentially been up by ferritic steel, which is based on iron, chromium, and so vanadium, like the Japanese people also try to be up. So we also have the project working on iron chromium under irradiation and also vanadium under irradiation. So here I'm showing only one example of tungsten, but essentially you're right. There are many other components which involve iron and also vanadium things. So certainly, but here I am showing only one example for tungsten.
Okay, thank you.
Thank you.
Thank you, Professor Duke, for a nice presentation and your very informative talk. Let's thank the speaker again. Thank you, Professor Duke.
Thank you.
Now it's time for the contributed lecture. So I request Sujoi Datta and Saumya to get ready for the presentations.
Yeah. So the next the two will be contributed oral presentations, and I request I request Sujay Datta from University of Calcutta to share his screen, share the screen of the talk. And the title of his talk is Electronic Structure of Configuration Average Two-Dimensional Random C2BN Alloy. Please start your presentation. Sujay.
Can you see my presentation?
Yes, it will be a 8 minutes talk followed by a 2 minutes discussion.
Okay, thank you. Good afternoon, everyone. The title of my talk is Electronic Structure of Configuration Average Two-Dimensional Random Graphene Boron Nitride Alloy. As we all know, graphene and boron nitrates are very well known today. System graphene is a zero band gap system, and boron nitride has a wide band gap. So from the very beginning, people tried to make alloys of them to tune the band gap. But experimentally, it is found that in many cases, graphene and boron nitride start to segregate. Even in the theoretical Monte Carlo simulations, similar kind of results have been found. Now let us understand there can be an enormous number of such configurations, and if we want to calculate the electronic structure from for those using the orthodox supercell method, then it will be impossible for us due to the computational time it needs. Let us understand what configuration means in case of alloys. A random alloy is always made by different configurations, and as we see in this picture here, we have nine sites for a random alloy made by three red balls and six blue balls, and here we can see there are at least 10 subsystems in this alloy, and in any experiment, what we get is the average results of all the configurations. And in experimental situation, we are not dealing with such small 9 number of atoms. There are several atoms, so the situation is much tougher. Next, we should understand the term spatial ergodicity to go forward with this. Ergodicity is well known in the temporal version, but spatial ergodicity is a thing when which we can say that in a large system which should have many subsystems, and every subsystem should represent an configuration that can be seen in this Monte Carlo simulation as well. If we take small chunks everywhere, we can see that small subsystem with a configuration is forming there. Now, how we can do configuration averaging? We can always do averaging on by calculating on separate systems and then doing the simple average. But the problem is that for n number of atoms, the number of possible configurations is of the order of 2 to the power n for a binary system, and it cannot be done. It cannot be done because n is very large. There is a mathematical trick which is called augmented space theorem. This is by Avijit Mukherjee long ago. This starts with the tight binding Hamiltonian, and each site can have either A or B type of atom in binary system. In ternary system, there are A, B, C, and something like that. And what we do in this, we take a random number which can take either 1 or 0. If at any site it is 1, then it is occupied by A, and if it is 0, then it is occupied by B. This is the very starting thing of this, and then we do a basis transformation. Basically, this n dimension, this is actually, when we are talking about a n atom system, this is an n dimensional space, and space and if and basis are the atomic basis. But when we transfer this in augmented space, this becomes every site at first is occupied by an average state, then fluctuations comes, and there are many mathematical steps which I should jump here. The basic thing, the main thing is augmented space recursion scheme can reduce the problem of configuration averaging to calculation for a single element of a matrix. That is the main trick, and it is becoming so fast for that reason. But we need tight binding parameters. Tight binding parameters can be extracted from DFT cores using 1R90, or from the site center based full potential nth Muffin-Tin orbiters also. Whatever we do for semiconductors, we should face a problem. The problem is well known. That is the band gap underestimation problem of LDA, non-empirical GGS, meta GGS, everything. A common solution is sorted from the HAC hybrid fractional calculation, or GW based calculation using the plane wave basis. An alternative and a very first way, as we see in this right panel, can be found, can be done using the VLB correction into LDA and implementing it in full potential NMTO system. We have done this on different types of materials, and we have found the success. You can see that MRE value, that relative error value is quite low for VLB NMTO. And being a site-centered based system, we can easily extract the tight binding parameter. This is the result for boron nitride. We can see the PZ downfolded bands.
Hello, Sujoy, you have 1 more minute.
Okay. The PZ bands are quite okay with the results. Using this, we can always calculate the variation of band gap for different concentration. This particular alloy is a special alloy because the carbon-carbon and boron nitride bonds are preferred, whereas boron or nitrogen-nitrogen bonds are not supported. And this is basically having some sort of short range ordering. And this is a general method which can be applied to any other alloy, quaternary alloy, basically. So we see that this is what we have seen in this. Using this method, we can do configuration averaging very fast and efficient way. I want to thank my supervisor, late Professor Abhijit Mukherjee, Professor Devnaranjana, my collaborators, Professor Dr. Prashant Singh, Manoj Kumar Harbola, and Duan Johnson. Thank you listening.
Thank you, Sujay, for a wonderful talk. It's a very nice presentation. And now is the one question by Professor Duke. Yes, Professor.
Hi. It's a very nice presentation. I would like to understand what you mean random configuration here, because you go to augmented configuration average. So what does that mean, random? Is that there any short range orders here? So I'm missing what you mean random.
Yes, this method is a general method which can be applied to any kind of random disorder system. Even we can incorporate the short range ordering in this. For this particular example, it has a tendency to short range ordering. That is why the segregation is seen. So we have applied this one. But in this 10 or 12 size, I just skip those parts for the random thing and for the short range ordering thing. There is the results are quite different. But I have just given a small brief introduction of that. Nothing else. It can be handled.
Maybe you use different terminology, because for random alloys there are no short range order, but maybe you treat the disorder configuration with short range orders. That may be more.
It's a disorder configuration, obviously. But the disorder can be homogeneous or inhomogeneous. If it is inhomogeneous, then there can be short range ordering. So all of these options can be handled in this methodology. The result is for the particular alloy which has a tendency towards the short range ordering.
Yeah. Okay. I just clarify the terminology. So I understand your talk. Thank you very much.
Thank you.
Thank you, Professor.
Thank you, Sujay Datta, for giving a very nice presentation. Let's thank the speaker. Okay, with that, we are moving to the last contributed talk, which is the contributed one of the session. And I would like to request Soma S. Bhatt from Indo-Korea Science of Technology to please share the screen and start the presentation. And the title of the presentation is Machine Learning Band Gaps of Orthometal Halide Perovskites. Soma, are you here?
Saurabh, it seems she has not joined.
Soma, no, I cannot see her actually.
Soumya, at best, I tried to call her and send mail. She has not responded.
Okay, so the last speaker, so she's absent. Okay, so what to do? So should we conclude the session, Dr. Surya?
Yeah, yeah.
Yeah. So let me conclude the session then. So I see actually already we are running half an hour late, so she's not here. That means she's not going to be here. Okay, so thank you again. I thank all the speakers of this particular session, Professor Kawazoe, Professor Duok, and I also thank the contributed lecture given by Shuja Datta. So we have very nice presentations in this session and also very good interaction. So with that, I would like to thank you all, and then I will hand over the session to Dr. Surya for any further announcement. Thank you.
Thank you, Saurabh. Thank you, Professor Kawasoya, Professor Duke, and Mr. Sujoy. So the session 1C has come to an now. So the session 2C, it starts by 5:30 p.m. So there we will have a wonderful talk by Professor Jedlai from Academia Sinica, Taiwan. So he will be speaking about the vibrational spectroscopy. So I request all the participants to join by 5:30. Thank you so much.
Thank you. Bye bye, Professor. Thank you.